Hi YouTube, welcome to a video on my channel 3D printers and a whiteboard. Today we will be doing something printer specific. We will be looking at the V-Core 3 made by RatRig and its bed leveling and frame squareness. The printer gets that used to be a flat bed before I did that. The printer gets shipped with one of those beds usually, which is a cast aluminum bed plate. Those are milled to high precision, which means the surface quality is usually in a way that the maximum deviation of the surface area is less than 0.2 millimeters. Of course, to make use of this precision, your printer frame has to be built accordingly. And this is what we will be looking at today. We will be looking at how to build a frame, a few build tips, then we will be looking at how to make use of a bed mesh and adjust your frame later. And we will also have a really small dive into how the printer actually constrains the bed leveling and such things. Let's have fun. Okay, first of all, we're going to have a look at the printer itself. We will start with the bed. The bed is suspended on 3 points here, 1 point here, and 1 point here. Mathematically speaking, 3 points define a two-dimensional plane and a three-dimensional space. This means there's exactly one plane that has all those 3 points, none other, and there's always exactly one plane when there are 3 points. Now, if we look at the gantry itself, we can see that there are more than 3 fixed points. It's a little bit discussable how many there are, but there are at least one here in every corner, making it 4. And then we've got the rail here, and there is an argument to be made that we can add more fixed points due to that, but we will let it stay with 4 of those points. In three-dimensional space, 4 points do not necessarily describe a plane, and that is the main issue we get with bed meshes. So, as a side thought, a super printer would be to build one with 3 corners, like that, with that shape, and then we don't have X, Y, Z rails, but 3 rails here, here, and here, and then we could do a bed mesh here, also suspended on 3 points, and then we could always find true leveling, assuming that those corners are flush, which then again is another issue of the printer, but it's, I think, a nice thought to have on the side for future printer designs if we're getting bored of Core XY. Yes, let's get back into it. So 4 points are over-defining a plane. So we can use 3 of those points. Let's take those 3 points and construct a plane here, for example. That does not necessarily mean that this point is in the plane. And when we are talking about squaring the frame, what we want to do is to make sure that after constructing a plane out of 3 points, that the 4th point is also on this plane. That's basically what is happening. Now let's have a look again at the bed mesh. And what does it do when we are doing set tilt adjust? Set tilt adjust is the way we make sure that this bed here gets as flat as it can get to the gantry. It compares to 3 points up here, one here, and one somewhere in the back here. Let's use a different color. That's a plane the printer builds, and then it just makes sure that this distance is the same for each point. And that's all it does, because it just assumes on set tilt adjust that this whole thing is a plane. And we are just looking at those distances. And if that's not the case, we see bent beds. What happens if we have those 3 beds? Let's get back. Maybe one more thought. When we have those 3 points building a plane, and this point here is a little bit lower, that would result in a mesh that looks something like flat in the front, and here it would look like something something like that. It would go up in this area after bed tilt adjust. So now if we look at the printer, we get a lot of constraints inside the printer, and a lot of things are not important to consider, but many things are. Now, what is important? It is important that this plane is actually a square. No, that it's actually flat, that it's actually a plane. And then we also want those angles to be right angled. This is important angle to be right angled. Then what is also important are those rails, those extrusions where the Z rails are attached, which are those three. So it is really important that those extrusions I marked red are all correctly built. That means correctly built means they are right angled where they should, they are parallel where they should, and not by any off angles. There are a lot more extrusions. There's this one, 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 that, and that. All of those I marked blue are unimportant. Those don't matter. They can as crooked as it gets. It does not matter. The only thing you may want to pay attention to as well is to make sure that those feet here on the printer, those feet, that they are also all sitting on the plane when your printer is sitting, so it doesn't shake or anything like that. But mechanically speaking, or in the kinematic system, only those red lines are important. So when we build the printer, we need to make sure that those are fine. Why are those those vertical lines important, you might ask? Those are not important for the bed mesh itself. Those are important for the layer stacking. Let's assume there's an off angle here, like we tilt this extrusion by an angle phi. What will happen is when we look at that on a sketch, this is right angled here, and we create an off angle phi, and we travel like 500 millimeters, for example. This is also 500 millimeters. We can see that the actual change in height is not 500 millimeters, but there's a delta Z, which is really easy to calculate. If I do that, let me see, sinus delta Z, that's delta X, sinus phi tangent phi times Z. Yeah, sinus phi times tangent phi times Z is the change in the height in comparison to the requested height, which means that your layers get squished. And layer squishing usually doesn't happen in a way that it's always squished the same amount, but the slicing will result in some inconsistent bulges on your print, which might be mistaken for Z-wobble, for example. Okay, now we know which parts to focus on while building the printer. Basically, the things we've marked in red are the important stuff, like the gantry and those three extrusions. Everything else can be screwed or crooked without having impact on your printing result. The only thing you want to make sure, in addition with the blue parts, is of course that when the printer is standing on the ground, that it doesn't shake, that it's sitting in a good position. And if you screw that one up completely here, it might not be the case. So, okay, let's start by looking at the tools we want to use. The first and most obvious tool, of course, are Allen keys for the screws. Then you want to have printed alignment tools for the linear rails. You want to have clamps and an engineering square. Building a square frame gets much easier by using proper tools. Proper tools means you want a precision square or engineering square. What you don't want to use is something like those things. We see those used a lot. You also don't want to use something that has is somewhat close to an angle, but it's not really an angle, or something like that. Is also something to keep away from your printer. That one as well. My son made it for me and I like it, but I don't use it for building printers because it's not working. What you want is something like this. And there you don't have to buy the pretty expensive stuff. In Germany, we have the DIN norms, which describe the precision of those, and an 875/1 is already enough for printing proper frames. Okay, now that we established the tools and which tools not to use, let's have a look at the building process itself. And therefore, I suggest to ignore the manual in that regard actually, and start by building the top gantry. Make sure those red parts are all in the right way, built in the right way by building them at first. Build the printer from top to bottom. Start with this gantry, put it on a flat surface and screw it together with those, those 4 corner vertical extrusions, of course. Then go on and make the rest. In the electronics gantry, when you're building that electronic chamber thingy, this extrusion can be later corrected very easily. Although it is one of those important ones being red, it's really easy to make sure that this is done well in a later process and can be adjusted later. Let's look at those two because it's easier to draw on. We are building this one and this one together right now. We want to use an engineering square. Clamp the engineering square to the extrusions because this way you make sure that while you torque the stuff down, it doesn't move again, because with the rotating T-nuts it can easily happen that you had it square in the first place, but when you screw it down, when you torque it down, it's losing its squareness. Torque it down in this order, please. Start with those 2 screws with light torque, then the other 3, then do the same thing with the end torque. The torque I suggest for the corner brackets is something 3 to 4 Newton meters, or something you can do with your hand. It's not important that they are really equally torqued. Just don't over torque it, because otherwise you will drive the T-nuts into the extrusions and possibly bending them, making it harder if you have to do corrections later on. The next thing you have to pay attention to is adding the linear rails. For the linear rails, use the alignment tools. It's really important that those are aligned well to the extrusion, because you can square all your extrusions if the linear rails are not attached in the same quality as the extrusions are. It doesn't help. So use the alignment tools, print 2 of them, put one on every side here. And then that is really important. When you torque down in the screws, start at one side and move to the other. Don't start by doing, the worst thing you could do is adding those 2 screws at the beginning and then work yourself to the middle, because this way you introduce stress in your system, and this gets much worse when the gantry heats, will result in a bowed gantry. The next thing is you don't want to screw the screws down with a lot of force. Like 1.5 Newton meters is already more than enough. You just don't want the rails to shake on the extrusion, nothing more. If you introduce a lot of stress by screwing them down a lot, again, the same thing will happen. If you heat the gantry, everything will be bowing. The next thing is, I don't think it is necessary to use all screws. I actually think it's better to use less, because there's one point where there are enough screws to hold everything in place, and every additional screw just has a high chance of introducing stress into your system. So what I do is using 5 screws for a V-Core 3 300mm build, and 7 screws per linear rail for a 500mm build. And that turned out to be a nice value in the past for me. One thing to mention is to not rely on the cut quality of the extrusions. We are working with corner brackets instead of blind joints, so we have the possibility to basically work with even really badly cut extrusions. Those extrusions are cut to a precision length of about 1 millimeter, absolute precision, but, and that is really important, the relative precision is much higher. So those 2 extrusions are cut at the same time at RatRig. Therefore, they are in the same machine, bent together, so they should be of equal length. But you have no guarantee that the end is actually right angled, so don't rely on that. When you're using the extrusions, try to sort the pairs which were being cut together. Usually it's all of those which are of the same length. Those 4 are cut together, and those 4 and those 4 as well. But There is no guarantee that something didn't need to be recut or something, and then make sure you find the right pairs and order them in the right parent. One thing maybe worth to mention is this specific extrusion here and this one. Those are of almost equal length, but not exactly. That means it's really easy to swap those extrusions up. This one is a tiny bit shorter, and if you use the one which is too long, you will push this one here up the extrusion and create issues during your build, so don't do that. Pay attention to that. One last and I think very important tip: do not attach the heat pad or magnetic pad to your build plate until the very last step, because you want to test your build plate first if it's okay. If it got, for example, a hefty knock on or knocked it on the table while you try to present it to YouTube before you build it in your printer, and the bed is damaged and needs to be replaced, you don't want to scrape off all the electronics, the heat bed. You don't want to scrape that off. That it's not a fun task to do, and it's easy to damage it on the way. So first analyze all the printer, do your print bed meshing, and only after that attach the heater pad. This is very simply done in the end, because you can lift the print bed out of its Maxwell mount without any issues, so there's no need to do that before you finish your printer. And one thing, if you're using the electronics back panel and the standard RatRig frame, make sure to not forget to add this panel at the right point of time, because if you do, it's really hard or basically impossible to install it in a later time without opening up the frame again. Okay, let's get into the last part, and I think the most important one. We are going to have a look at adjusting your frame after you build it. So you build your printer and you do run your first bed mesh and you get that result, and that is pretty much very disappointing. You can see some deviation of more than 1 millimeter over the print bed on what is that, 400 millimeter V-Core 3. And that of course is too much, but we can already see that this is mostly frame related, not bed related. And let's see how we check that. First of all, we want to name those corners we are working with, and I'm going to name them A, B, C, D. When we do Z-tilt adjust, we already established that in the past. We know that this and this distance will be the same at the end. And we can actually see that in the print, in the result here. Somewhere in the middle, in the back, it's exactly on the plane, as well as those two outer points. But this point here is way too high, and the left bottom corner, so it's way too high here, and the bottom part is way too low. Way too high in this case on this graph means that the bed is too close to the gantry. So if the bed is too close to the gantry, and we need to adjust the gantry to compensate for that, of course, we need to bring up that gantry. But we don't want to touch the C and D part. We don't want to touch that for multiple reasons. The reasons are basically the motor mounts are making it harder to adjust in this corner, but more importantly, this additional extrusion here, the electronics compartment, makes it really hard to push it, for example, down. Although pushing up would probably work. Instead of pushing that one up, we can also push down the front, and Z-tilt adjust will compensate for that. And yes, that's basically the whole idea about adjustment, is to get those 2 points on one plane. Those two will always be on one plane, because Z-tilt adjust makes sure the mid here as well. So if those two are on one plane, we know all 4 points are. When all four points are on the plane, that means we are as parallel as we can get with the 2 planes of the bed and the gantry. Okay, so what are we going to do? Again, on the back right corner C, we could also A, B, C, D, just for comparison. Okay, so on the C corner, the bed is too high. That means we're too low with the gantry. We need to move the gantry up, but we don't want to do that. We want to adjust B, so we push B down. And that's basically what you always do. You just look at one of those two corners and then you push that down. How do we push that down? We unscrew this screw, this screw, this screw, and that one. And then we give it a gently tap from the top with a rubber hammer or something like that. Then screw it back together. And if you did that, rerun your bed mesh. When you rerun your bed mesh, don't forget to rerun Z-tilt adjust as well, because otherwise you will get bad results. So this is this bed is actually covered with that almost. So let's look at a few other beds and what we can see there. So this is another bed mesh. That one I just pulled from Discord actually. First of all, let's establish which corners are which, because that's a little bit turned. That's 1A, B, C, D, and we see the same thing here. The bed is too high on C. That means the gantry is too low on C. That means we need to push down B. And that's actually the thing we most commonly see, is that C is up, and that mostly is due to the fact how the manual works with the order of how you build the frame and attach the motor mounts and such things. And that should already be better if you follow my instructions by starting with the top, but it will still be probably not perfectly square, so you want to do that. Maybe just to throw in the middle, I think a good goal is to have a 0.2 millimeter deviation over the whole bed. So here we are looking at another V-Core 400. Let's first, again, as always, establish the corners. That's corner A, B, C, D. And, well, we can have a look, and we can actually see something good. The deviation is already really low, 0.2 millimeters max deviation. And those corners are almost at the same level. But we have some bowing to the middle. So bowing to the middle means that your gantry is bowed in this direction. So we have bowing here and bowing here. And this is one of my, if I'm not mistaken, I think that's a bed mesh I made, and that's my first printer I built from the V-Core 3 series, and I didn't pay a lot of attention on the linear rails. It was a long evening, I was tired, just screwed everything down, I think even with an electric screwdriver, to be honest. And that's the result you get then. This bowing is when you heat it up, it slightly bows. And yes, what you need to do is loosen your linear rail, reattach it in the screwing order I told you, and then this bed mesh will look much better. And be even better than 1.2 millimeters difference over the whole thing. You could see that there's also delta Z, and this here, so there is the possibility to, again, all my examples today are pushing B down for some reason. Push B down a little bit, but I think that difference here is like, yeah, really low, maybe 0.07 millimeters or something like that. That is something I usually ignore. But it can be perfected, but that's the level where I stop with the adjustments. So here we can see another thing. We can see a bed mesh that looks actually like bowed like that slightly, which means that the gantry would need to bow downwards, or the bed to bow upwards. So this is most likely actually shape of the bed itself, and it's still very much okay. And this is actually a bed on one of my printers which was not made by RatRig, so they are not to blame for that one. And then we have, of course, this really high peak here. And that's suspicious, because it doesn't really make sense on manufacturing that you create something like that, if you take care at least. This could be two things. One thing, something bumped in here and created a compression point, which pushed it up. But most likely, when you see something like that, lift your magnetic sheet and see if there's some debris between the bed and the magnetic sheet. And well, in this case, I browsed through my printers to find a few bed meshes to discuss here, and I found that one, opened it up, and it was a small piece of brim that was stuck between those two things and lifting it up in the corner a little bit. So if it's in the corner, it will create those really sharp peaks just because the sheet metal allows bending there. This is another bed mesh I pulled out of this quote, and we can establish the corners again. It's A, B, C, D. Now that I look at it, I pulled it from our RatRig V-Core, but that seems to be a Warren printer. 120mm bed size kind of suggests it's a Warren V0. So I didn't pay a lot of attention there, but still we can learn the same things. What we can see is that this bed is almost perfect in the corners, which makes sense on a V0 actually. And a really tiny printer, which allows good gantry leveling. But we also have this like bump in the middle. And this bump in the middle usually is the same thing as the sharp thing we saw before. That's some kind of debris. And in this case, I think the user wrote it was a precision shim which was stuck between bed and a print sheet. So those kind of things happen as well, especially as the magnetic shield, of course, likes to collect things that drop down and are made of metal. Yes, and finally, so this is a print bed that for my taste is perfect now. You can still see some kind of shape on it, but look at those numbers, they are really, really low. The maximum deviation is like 0.07 millimeters. So that's really good. So what we need to keep in mind is during bed meshing, we also have some errors on the mesh with the probes. And then we have the magnetic sheet, the metal print sheet, and this also has a slight shape to it. So that's probably that. You can't blame anything with that one. So that's it for today. I hope it helped you to get your bed mesh to a good level. If not, please feel free to ask either in the comments or on the Discord server, and we will always try to support you there. Have a good time.